Hi folks, welcome back to the second part of Lecture 7 in the Experimental Design and Analysis section of the Core Skills modules. So before the break we had a very long, I'm afraid, section about chi-squared. Now we've got a slightly simpler job. We're going to switch tack completely, moving from looking at differences to looking at trends, and we're going to look at correlation in particular. So hopefully this won't be as long as the previous chunk. And the learning objective that we're really targeting here is that you need to know about two different ways to test for a correlation and understand when they're appropriate. So we've got a parametric version of the correlation test and a non-parametric version which doesn't make the same assumptions. But initially we're just going to start off by comparing correlation with an alternative type of analysis for this sort of situation, something called regression. Okay, so trends. We've spent a lot of time dealing with differences, looking at differences between means, or in the previous section, differences between frequencies. But very often in the life sciences, we're interested in actually trends between continuous variables. So visualized on a graph, this sort of thing. We've got two variables. We want to know if there's a positive correlation or a positive association of some sort between them, or a negative one, or no association. So when one variable increases, does the other variable tend to increase or decrease or do nothing? So the alternative hypothesis in this situation is going to predict a trend. It's going to say there is a relationship between these two variables, while the null hypothesis says there is no such relationship. So the expectation under the null hypothesis is that you're going to see the sky at night, if a random scattering of dots on your scatter plot in the long term. So those are the hypotheses that we're looking at using the kind of analysis we're going to talk about today. But it's important first of all to distinguish between two different scenarios when we're looking at these kinds of associations. There are situations in which we expect a causal relationship. So there's a pair of variables, a kind of x and a y, and they're not equal. In other words, one of them is expected to drive the other one, to cause the other one to change. This is a causal relationship. And this is very common in the life sciences. So let's imagine we're looking at growing sunflowers and we want to know what conditions are ideal for producing the tallest sunflowers. We could do an experiment where we manipulate the amount of water available or the amount of nutrients available, and then we could look to see how well our sunflowers grow. So we're looking at a situation where we have two continuous variables, let's say quantity of water and the height of the sunflower. But there's an obvious causal relationship between these two things. If there is a relationship, it's going to be because the amount of water that you add to the sunflower causes it to grow better or worse. Not the other way around. You can't imagine how tall a sunflower grows is going to affect how much water you apply to the sunflower sometime earlier in the year. It doesn't make any logical sense. So there's a causal relationship and it goes in one particular direction. The x variable causes the y variable to change. So we will always put the causal variable on the x-axis, in this case the amount of water that we added, and the response variable is on the y-axis, the growth of the sunflower. Causal relationships are explored in lots of different ways, but in some situations we actually want to make a prediction based on the an analysis of that causal relationship and predict what will happen to y in the future if we manipulate x further. So from my point of view, as an ecologist, I'm interested in climate change and all its various impacts. We might be interested in how temperature affects the proportion of alligators that are male. Just to continue our theme from earlier in the lecture, you may be aware that some reptiles, their sex ratio is influenced by temperature. So if you incubate the eggs at high temperature, you get all males, and at low temperature you get all females, or vice versa. So we could have a look at this relationship in a laboratory experiment where we manipulate the temperature and record the proportion of eggs that are male, and we could then make a prediction about what that might mean for climate change. So if the world warms up by 2 degrees, we could predict what will happen to the proportion of alligators that are male. So in this kind of situation, where we have a causal relationship which we may or may not want to predict, we're going to need a different kind of analysis from the other situation that we encounter commonly in the life sciences, which is where we are simply looking for a pattern between two variables. We don't know about the cause and effect, or we don't think there is any cause and effect. We think instead that the relationship, if there is one, will arise because of other causal variables, kind of confounding variables. In these situations, we need a different test. So just what kind of situation do I mean? It's perhaps not immediate, especially if you're used to thinking about experimental science. It's not immediately obvious that correlations like this are interesting very often, but actually, particularly in observational studies, we get this situation a lot. So this is something that's close to my own heart. What we've got here is chocolate consumption on the x-axis for each country in the world, and here the number of Nobel laureates that there are in those countries per capita, or per 10 million people in the country. So Nobel laureates, people who've won the Nobel Prize, these are super clever people who've done amazing things in science or the arts, and the graph here is suggesting that there might be an association between the ability of a country to produce these amazingly brilliant, brainy people and how much chocolate they eat. So, for example, Switzerland, unsurprisingly, those guys eat a lot of chocolate and they have loads of Nobel laureates, so they are really highly likely to produce people that win the Nobel Prize. Whereas down here in China, Japan, Portugal, relatively few people eat chocolate, they eat small amounts of chocolate, and they don't seem to win Nobel Prizes. So we've got an association between these two variables. It seems pretty clear, actually, but that doesn't mean that one causes the other to change. It's actually pretty unlikely that eating chocolate makes you a genius and therefore you win a Nobel Prize, and it's also pretty unlikely that if you're a genius, that makes you eat more chocolate. So the idea that one of these variables causes the other to change is pretty laughable. Instead, this pattern that we can see, it's still a pattern, it's still there, it's real, tells us something else, and it tells us actually about other causal variables. So the most obvious explanation for this pattern is that rich countries that can afford to buy lots of chocolate, particularly rich European countries where there's a history of eating chocolate, lots of wealth, and a history of doing lots of science, really well-educated population, ergo they tend to win Nobel Prizes. So there's a sort of hidden causal factor here, which is variation in wealth, that is causing both of these variables to change, and that gives rise to the pattern that you can see. So there may be a causal relationship between these variables in this kind of situation, but we don't know what they are. We don't necessarily expect there to be a causal relationship. We wouldn't know which variable to put on the x-axis and which to put on the y-axis. So typically these situations arise because of these other causal variables that aren't in your graph, as it were. And a kind of classic example of this is a real result that came from the natural world, which suggests that human babies are more likely to be born, or there are more human babies born in years following years in which there are lots of storks arriving in. This is from Northern Europe, I think it's a study from Denmark. So if you look at the summer arrival of storks in Denmark, they come and nest on the tops of buildings. If you get a lot of storks in a particular year, the following spring you seem to get lots of human babies. There's a correlation there. How can this possibly work? Now, there is a causal hypothesis that storks carry babies, as in the old myth, but as good biologists we know that's nonsense. So what's really going on? Well, actually it turns out the real cause is climate. So warm years, warm summers tend to attract lots of storks and tend to correlate weakly, not very strongly, but weakly with human fertility and the likelihood that humans will have babies. So there's a pattern arising as a result of a shared causal variable, but the two variables we've measured, numbers of storks, numbers of human babies, don't have a direct causal link, and it's not obvious which would be the x and which would be the y in our relationship. Okay, so these two scenarios call for different kinds of analysis. Where we have a causal relationship or we expect one, then we're going to use regression analysis, which I'm going to talk about later in the course. Where we're just looking for patterns, we're just looking for associations without any particular feelings about cause and effect, then we're going to use correlation analysis. So that's the key distinction. So correlation analysis detects the relationship between two variables using a thing called a correlation coefficient, which is a statistic. So there are two correlation coefficients we're going to look at. One is a parametric statistic, that's Pearson's correlation coefficient, normally given lowercase r, and this is a parametric stat. The alternative is Spearman's rank correlation coefficient, which is typically indicated by this Greek letter rho, which looks a bit like a P but kind of slightly smoother, spelt RHO. And this is a non-parametric correlation coefficient, so when you do correlation with Spearman's rank, you don't make all the assumptions that you would otherwise make. So let's look first at the parametric test. So just like the other parametric tests we met last semester, Pearson's correlation makes a bunch of assumptions. It assumes that the data are continuous. So that might be a bit of an issue if you've done, like say you've counted the number of stalks. Technically those are discrete data, but as I said earlier, count data like that can be treated as continuous under many situations. Crucially, you're going to assume that the data are normally distributed, and we've seen that sometimes that isn't the case. And you're also going to assume that the relationship between x and y is a straight line, which is not always the case either. So making those assumptions, if they are valid assumptions, we can go ahead with a Pearson's correlation test. Your computer will do it for you. It will generate a test statistic called R, Pearson's correlation coefficient, and a p-value, just as normal for any other stats test. So what's R going to tell us? R is going to tell us about the strength of the relationship between our two variables. When R is 0, you must be looking at a situation in which there's absolutely no relationship between x and y. So you're going to see this sky at night, random dots on a graph. But if there's a strong positive relationship between x and y, you're going to see R rising above 0 towards 1. So 1 is the maximum. Here we've got a relatively strong correlation with a correlation coefficient of 0.66. So there's a relatively tight positive relationship between x and y. If R is negative, then we see the opposite. So we see here with R as minus 0.7, a relatively strong negative correlation. And at the extremes, when R is exactly 1, then what you're saying is there's a perfect relationship between these two variables, that any increment in x will generate exactly the same, and it will generate an increment in y completely predictably without any noise. So that's what a perfect correlation looks like. So when we run a correlation test, we're going to generate this R value and a p-value to go with it. And the p-value says what's the probability of observing this tightness of relationship for a particular sample size if the null hypothesis is true. So there'll be a relationship here between the sample size, the R correlation coefficient, and the p-value. Basically, the stronger the correlation you've got, the less likely that is under the null hypothesis, so the p-value will drop. But also the bigger the sample size for a given value of R, the less likely it will be that that's happened by chance. So if we compare two situations, here's a situation with a large sample size, a relatively large sample size, and quite a strong positive correlation coefficient. The probability of observing this relationship by chance is very low, less than 1 in 100. Imagine if you kind of were throwing darts at a dartboard blindfold, the chances of you getting this nice positive pattern at random, well, there is a possibility it could happen, but it's very unlikely. It's less than a 1 in 100 chance. But just to show you that, as we've said before, there is this relationship between significance, effect size, and sample size. When you have a really small sample size, so here we've just got, 8 data points, then you can get the same kind of apparently strong positive relationship between two variables when it's still quite likely to have happened by chance. So if I throw 8 darts at a dartboard, there's a reasonably high chance they'll end up looking like this with apparently a positive relationship of 0.7. Specifically, we can use the computer to tell us exactly how likely it is. In this case, there's an 8% chance of seeing a relationship at least this strong if the null hypothesis is true. In other words, there isn't really an underlying relationship. So that's how correlation works, and we'll just have a very quick look at a real example, one that's close to my heart. My PhD supervisor was very topical for today, but he was an epidemiologist interested in particularly the relationships between different infectious diseases. So he was looking at the relationships between measles and whooping cough. And this is all very relevant in the world of COVID, because measles and whooping cough are effectively competing for human hosts, or at least this was the hypothesis. And during the 20th century, before the advent of the MMR vaccine and the whooping cough vaccine, these diseases were rife in the human population and they killed a lot of people. So they were a huge problem. And this is one of the reasons why MMR and the whooping cough vaccines are so important to take. At this point in the lecture theatre, I'd normally ask you whether you've had these diseases. Nowadays, almost nobody's had either of these diseases. I've had both. I had measles twice. And then whooping cough. I had whooping cough because I missed the vaccine, because there was a vaccine problem when I was at the right age. So it kind of illustrates this issue that vaccination really is so crucial. But yeah, my supervisor was interested in this relationship. So when there were major outbreaks of measles, it looked like there might be slightly less whooping cough around and vice versa. So we're going to look at this hypothesis that there's some kind of competition between measles and whooping cough. If you get sick with measles, your immune system goes crazy trying to get rid of it, and that potentially makes it more difficult for whooping cough to get into you, as it were. So you can imagine this might work with COVID too. Maybe when you've got COVID, you're maybe less likely to get a cold, for example, if your immune system is busy fighting off COVID. So we can expect possibly this kind of competition between diseases via your host immune system. But we don't know, we need some data to support it, so we go looking. And what we're going to do here is look at death data from the early part of the 20th century from different cities in the UK and look to see whether there's a negative association, which is what we might expect, between the two diseases, or whether instead the null hypothesis is true, that there's no relationship between the numbers of deaths caused by measles and whooping cough. So it's a big data set, we've got lots of data. And if you plot it on a graph, I've sort of simplified the data here, but this is roughly what you see. It looks like a big cloud of points, but there is a weak negative association here. It looks like there is a bit more measles when whooping cough is rare and a bit more whooping cough when measles is rare, but it's not very clear. But we've got a huge sample size, so we've got a lot of statistical power to test this relationship. The R value here is negative because it's a negative correlation. It's 0.27. Chuck this into a computer, it will tell you R, and then it will tell you that the probability of seeing that weak negative relationship by chance, if the null hypothesis is true, is actually less than 1 in 100. So we would conclude this is a significant relationship. Measles and whooping cough are indeed negatively associated. We'll reject the null hypothesis, we've got a correlation. Now, whether it's causal is a bit more difficult to ascertain. Does whooping cough prevent measles from getting in, or vice versa, or both? Or is something else going on? Maybe when populations are vulnerable to measles, they're not vulnerable to whooping cough. It could depend on all kinds of economic and behavioural factors that we don't know. So I used correlation here because I'm not sure what way round the causal relationship might be, if there is a causal relationship. Okay, that's the end of that part, and we're going to come back and have a look at the non-parametric equivalent of that correlation in a moment.